Well, this lesson is about the basic concepts on how to graph and transform the trig functions. Now, before we go ahead on the graphing part, I'm just going to quickly recap some of the transformations that I'm going to use. So in case if you have been given y equals to f of x graph. Now, when you say these transformations, so suppose the first transformation is f of x plus a, it means the graph moves a units up, provided the value is positive. If f of x is, if it is f of x minus a, it moves the graph a units down. If it is f of x minus a, it moves a units to the right, provided a is positive. And if it is f of x plus a, moves a units to the left, a units to the left. If it is f of negative x, its reflection across y-axis, reflection in y-axis. If it is negative of x, its reflection in x-axis. So the other two are very important stuff, that is vertical stretch factor. If it is AF of x, it is called vertical stretch factor by A. So it is vertical stretch factor by A. If it is f of ax, it is horizontal stretch factor by 1 over a. So here, just be careful if it is f of 2x. So whenever you replace x with, let's say, ax, it is there will be the new x values will get divided by a. So if I have a graph like f of 2x, each of the older x values gets divided by 2. So it's like each x values multiplied by half. So that's why we call it a horizontal stretch factor by half. Now, what I'm going to do is I'm going to first quickly remind the technique by which you can draw a basic sine and cosine graph without referring to any source. So the source reference here that comes is when you have a unit circle that I have drawn here. So the coordinates you got to write. And if I consider any angle, which is the reference x-axis, I'm just going to quickly mark my x and y axis. So assuming that this is the x-axis, this is your y-axis, and I'm going to quickly mark the points now. So let's say this is 0, 90, 180, 270, 360. And here I'm going to take negative 90, negative 180, negative 270, and negative 360. So now our step is to find out the values for these angles. Now, as you know, that cos theta comma sine theta is a general coordinate that, as I have made clear in my first video on the unit circle. So the x coordinate is cos theta and y coordinate is sine theta. So my first objective is to graph sine theta. So when you graph sine theta, the first value which you get is sine 0, which is y coordinate. Sine 0 is 0, that's why it starts from 0. And the next part is to go on to 90 degrees. So sine 90 is actually 1. So sine 90 is 1. 180 is 0. And 270 that you get is negative 1. The 270 is negative 1. And 360 is 0. Now, if you go clockwise, which is minus 90, that is negative 1. Then negative 180 is 0. You can see clearly. Negative 180 is 0. Negative 270 is here. Positive 1. And negative 360 is 0. So when you draw the graph of a sine curve here, it looks like this. So this is like a periodic graph with a period of 360 degrees. So what is the time period for sine? So time period for sine graph is from here to here. Either you take this distance, or you take from one maximum to the other maximum, which is also going to be 360 degrees, or one minimum to the other minimum, which is 360 degrees. Or you can do a max to min, which is, let's say, 90 to 270, for example, here. And then you double that. So if you're finding, let's say, time period using max and min, this distance, what you got, double of this is a time period, because actual time period is one max to the other max. So this is the basic sine graph, and the cosine graph can be also obtained in a pretty similar way that I have shown down here. So let's just have a quick look at that. So cosine graph also can be obtained in a pretty similar way. That is this green graph that can be seen as the cosine graph. And the logic is pretty simple. The logic is here we use the unit circle to draw both the graphs. So first, let's just make sure that we register these at least one cycle of each sine and cos graph in our mind, because lots of times when they give that, okay, you sketch the graph from, let's say, 0 to 360 degrees, let's say 0 and this is 360, and you sketch at least one sine graph, one cycle of sine graph, it means you should by heart know at least one cycle of sine and one cycle of cosine, and you should also know where do they cross x-axis. That is really interesting and important. Now let's just have a quick look at the transformation steps. How do we transform the graphs and what are the effects of those? And then we'll do real life modeling questions from exam papers. Well, so let's now just have a look at how the transformations um, are actually gonna be shown on the sine cosine graphs. So let's say I take my original graph is sine x graph that I'm going to take first to investigate, and I have kept the setting for this graph on the Desmasa in the degree mode, so you can see the degree measurements. And what is going to be really interesting is you got to see how actually the cycles, each cycle of the graphs and the amplitude of the graphs change. So first I'm going to show you the original sine x graph, which is, let's say y equals to sine x. So let's say when I have got f of x equals to sine x function. So original sine x graph that you notice is actually has an amplitude of 1. If you see, this is the amplitude, and the time period is 360. So if you see that this same cycle is identical here, so it's like you can cut this part and this is going to be identical throughout. So this is the basic part of the sine and cos graphs, that is time period. Both the graphs are time period as 360. So its original time period is 360. Original amplitude is 1. Amplitude is 1. Original range of the graph is -1 to 1, both inclusive. So these are some of the things. And the domain of the sine x is, of course, it is x belongs to real numbers. So now let's begin the first transformation. I'm going to investigate the effect of a on the graph of sine. So let's see, the first graph is a sine x. So I'm just going to add up a slider, y equals to a sine x. Now, when you do that, you notice here, if an a is 1, is actually the same original graph, of course. And then if you put a is 2, or a is, let's say, 3, for example, here, if I'm putting a is 3. So now what you notice is that the amplitude of the graph is actually now at the same point, it is vertical stretched by a factor of 2.9, since my a is 2.9. So the amplitude also becomes 2.9. So whenever you have such situation, so a is your actually the amplitude, or you can say a is your vertical stretch factor. So a is the amplitude or vertical stretch factor. Now let's check about the investigation about the b value. What does b do actually? So when I do that, if I look at the first graph, I'm just going to hide it up. Now, second that I pick up is the b, the value of b. Now, if I take the value of b as 1 here, now what you notice is this is the original sine x graph. So if I take b as 2 now here, what you notice is that the graph that you had earlier now earlier had the red graph, if you notice, is had the time period of 360 degrees. If you see, one of the cycle that you can see clearly had the red one had 360 degrees. Now the same blue graph is completing its time period is 180 degrees. So actually what's happening is this, when you do sine of 2x, it reduces the time period by half. So if it is sine 3x, it will reduce the time period by 1/3, because it's a horizontal stretch factor by 1/3. Also, you can see that there's this, if you notice, this is b that you see here, b is actually the frequency. Because if you see in the same 360 degree, you've got now how many cycles? There are 2 cycles of the sine 2x graph. Similarly, if I show it to you about the sine 3x graph, when you notice here, if I make the value b to 3, you'll notice that there are three cycles of the sin x graph. So when you look at now here, the graph actually has got the 3 cycles in the same time period. So when you look at this part, which is here, one cycle ends here, that's 120, another cycle 120, and the third cycle is 120. So this is how you basically take care of the b value. Now, if you have a particular graph already given and you know the time period of the graph, so b is 2 pi by new time period. This is a formula. Or you can say that new time period is 2 pi, or basically 360 if in degree radians, I mean degrees on radian, vice versa. So 2 pi by b is the new time period, or 360 by b is the new time period. So this is about the time period and the effect of b. Now effect of c is pretty simple. It moves to the right or left. And effect of d is, it is, now let us just quickly check. So effect of d is when I say, let's say here, I'm going to keep b and I'm just going to add another slider, which is d. So you can clearly see that the effect of d is that it moves the graph up and down. So clearly, so this is the effect of uh, a, b, c, and d in terms of transformation. Now there are some shortcut formulas that you can remember. The formulas that are there for this, finding the missing values a, b, c, and d, sometimes when the graphs are given to you, is actually, when you look at a, is actually the amplitude, which is also given by max y minus min y over 2. B is 2 pi by new time period. So B is 2 pi by new time period. That's the other formula. C is the shift to the left or right that you can obtain, like using the general, like the general shift, or you can say the general comparison of the graphs. So if you compare, okay, the origin should be here, and here in this graph, the origin is also here. I mean, there is no shift. Okay, there are some textbooks which write down the formula is the first minimum, x minimum, where for which the y value is minimum, and the x maximum for which the first x value for which the y is a maximum. So you take the average of these two, and that's your C value, which I'm pretty not sure of this because sometimes it works and sometimes it doesn't. So when it is, I'm just going to probably take an example and verify this. So right now, let's not write down this as a formula. So we got the C by observation, and D you get by max Y plus min Y by 2. So this is the formula for A, B, C, and D. The same formulas are also valid for the cosine transformation. And the only difference that you notice for the tan transformation is that A is referred as a vertical stretch factor. B that you get now here, B is actually pi by new time period. Now, if you see new time period, so I'm just going to show it to you the tan transformations in a bit. C is the shift to the right, and D is the shift up and down. So this is the basic graphs, basic transformation of sine and cosine. Let's have a quick look on the transformation of the tan graph and how does the original graph of tan look like. And after that, let's take some problems on graph transformation. So here's the transformation of the tan graph. So I'm just going to first show you the original graph of the tan x function. So as I said that y equals to tan x graph, firstly here you got to be very careful that wherever you got the cos x 0, that's where you get the vertical asymptote, because tan x is actually sine x over cos x. So wherever your cos x is 0, that's going to be your vertical asymptote. Now when you look at this point here, which is the roots, that's where the sine x is 0. So now the one cycle of tan graph is actually from here to here that we take. That's negative 90 to positive 90. So time period is actually 180. You can see this identical cycles are repeated everywhere. So time period of sine is 180 degree, tan x is 180 degree. So when you do the a tan x graph, a tan bx, let's say plus, let's say minus c and plus d. So now A is your amplitude for the general sine and cos, but for tan, there is no amplitude. As you can see, this is just an infinite range you have. So A is actually referred as the vertical stretch. Um, B is the new time period that's get affected. So B is actually pi by new time period, or you can make vice versa the subject. So new time period is pi by B, and C is the shift to the right or left, and D is the movement up. So that's what is the general transformations of the tan x graph linked to. Now let's just have a quick look at how do we actually how do we visualize it on the graphs when you have got the transformations. So I'm just going to quickly remove these vertical asymptotes, and let's have a look at the transformation. So when you have y equals to, let's say, 2 tan x, so you can see that the graph, the red graph, is actually the transformed graph, which is vertical stretch. So each x value remain the same, and their y value gets double. So that's why there is no amplitude here. Then if you got the, as far as the time period is concerned, here if I have got tan 2x, so if you got tan 2x, you can see that the graph got stretched by a factor of half. So here the asymptote was at 90, but here it is at 45. So now the time period also got reduced to half. So this time period is 90, while this earlier was 180 degrees from here to here. So logically speaking, this is affects the time period. So as I said, that the uh, new time period is 2. Here it is pi by b, which is pi by 2. So for tan 2x, it is that way. Tan 3x, it will be pi by 3, and so on. So now when you do the vertical stretch and this thing, that visualization is a very important key here. Now when you look at the movement up or down, or for example, if I got tan x plus 5, so the graph actually moves up by 5. Okay, so the graph moves up by 5 units here. So here in this case, you can see that this point actually the asymptotes are still the same, but the graph is actually just moving 5 units up. So these are the transformations linked up with the graph. Now let's take one IB exam question that can help us uh, solve and understand this topic better. So let's take IB example from the standard level past paper. So let's say they have given that this is a trig model that is having a maximum value when it is 3,29, and the minimum value is at 9,15. So this is 9,15. Now they say that somewhere, if you see here, they say that this is a cost model, and it is a cos bt minus c plus d. So a cos b, so a cos b t minus c plus d. Now let's just find out one by one the values. So a, that as I spoke about earlier, this formula is max y minus min y over 2. So max y is 29. So 29 minus 15 over 2, that's here 7. Now the value of b that you notice here, the value of b is 2 pi by new time period. So new time period of the graph that you can see here, it is that this distance, actually I'm going to find out this distance, that is vertical distance here. So vertical distance is, this distance is actually 6. So the time period is actually going to be 12, because time period is one max to the other max. So the time period here is 12. So this is 2 pi by 12 is your value of b, that is your pi by 6. Now comes the value of, let's say, d. We'll find out c by observation, but d is the max y plus min y over 2. So when you find out the max y plus min y over 2, which is 29 plus 15 over 2. So this is 4, this is 44 over 2, that is 22. So the value of d that you notice is 22. And also if I draw a line somewhere here, that's where, what is your d value. So this is actually the midline equation that you got. Now as far as the c value is concerned, when you look at the observation, the cost graph, the original cost graph is actually having first maximum at origin. Now here the first maximum is at 3. It means that the graph has been dragged by 3 units to the right. So the C value that I take is straight over 3. So that's how you find out the values of A, B, C, and D. And now let's take some more example for this kind of concept.